Section 10.6 is about exponential growth and decay. We're going to look at formulas that scientists use to find how things grow and how they decay, and those formulas are exponential functions. Here you see exponential decay is when a quantity decreases by a fixed percent each year or some other period of time. This is what the formula looks like, and each letter represents something. So in the formula, the y is the amount of the decrease, how much it decreases. T is the time, and we measure that in years. A is the initial amount, where it started, and R is the percent of decrease. When you put the percent of decrease in, you're going to put it in as a decimal. Now this R is also known as the rate of decay. So if a problem says the rate of decay is so-and-so, then that's what you're going to use for the letter R. So this is the formula we're going to use to find exponential decay. Here's an example. It says a cup of coffee contains 130 milligrams of caffeine. If the caffeine is eliminated from the body at a rate of 11% per hour, how long will it take for half of this caffeine to be eliminated from a person's body? So here's the formula for exponential decay. It has 4 variables, and we're going to look at each one of those. First one we're going to look at is the time. We're told that the body eliminates caffeine at a rate of 11% per hour. Now, one thing that I told you on the last slide is that time is usually measured in years. If it specifically says some other form of measurement, then you're going to use that. So here we have the amount of hours, and that's what we're trying to find, so we don't know what T is. The Y, which is the amount that it decays, is half of 130 milligrams, so that's going to be 65. The initial amount, where it starts, is 130. And the rate of decay, we're told, is 11%, so we're going to use 0.11. So these are the values that we're going to plug in, and we're going to try to find the time. So here's what it would look like. I want to isolate this t in the exponent. I'm going to start by dividing both sides by 130. 130 is half of 65, so this is 0.5 equals, and then 1 minus 0.11 is 0.89 to the t power. Now the way for me to get the t power down so that I can solve for it is I'm going to take the log of both sides. And now one of the properties of logarithms is a power property. That means I can take the t and put it out in front of the logarithm and multiply it. So that brings the t down from the exponent and makes it something that's being multiplied. Now why is that nice? I can now divide both sides by the number log of 0.89, and I can isolate my t. So these will just cancel, and if you plug this into your calculator, you get approximately 5.9480. So that's about the time it takes for half of the caffeine to be eliminated from the body. So if we answer the problem, how long will it take? We'll say about 6 hours. Now there's another model of exponential decay that scientists prefer, and you see it here, and it's interesting because it has an E in it. We're going to use this example because it further illustrates how to deal with exponential decay. Now if you read this example, you'll find some things in here where it talks about the half-life of carbon is 5,760 years. Now personally, I don't agree with some of these numbers, and there are many scientists that argue about the half-life of some of these materials. It all depends on what your worldview is, and my worldview is a biblical worldview, and I don't buy some of the numbers that they use here. I'm going to use this example because it helps us see how to deal with the exponential decay, but just understand that I don't buy some of this from a factual standpoint. So here's our formula. Y equals A base e to the kt power. Now k is some constant, and that's what we're trying to find. We're trying to find the value of k for carbon-14. Now since A is what the carbon starts out as, we don't know what the initial amount of carbon is. We also don't know how much carbon is decayed during its half-life. But we do know that it's half of what the initial amount is. So instead of y, I'm going to use 0.5a, because that would be half of what the initial amount is. Now E is just the value E that we've been looking at. We're trying to solve for K, and we're told here that carbon has a half-life of 5,760 years. So that's going to be the time that we're going to use. And our goal now is to solve for the K. Remember, E is just a number, 2.7, so that's not a variable we're going to solve for. I have a's on both sides, so I'm going to divide the left side by a and the right side, which will cancel those off. So now we have 0.5 equals e to this exponent. I would like the exponent to be brought down. Because I have a base e, the opposite of base e is the natural log. So I'm going to take the natural log of both sides, or the ln. Now because the natural log and the natural base here cancel each other out, I'm left with ln of 0.5 equals negative 5,760k. So now I've basically brought the k down so that I can solve for it. So we'll divide now by this number and isolate the k. And if you plug this value into your calculator, you'll get an estimated value of 0.00012. That is the constant in the exponential decay formula here for this situation. So if I were to plug that back in and write my formula for carbon, it's going to be negative 0.00012 times the time in years. That's what the formula would look like for carbon-14. So now we're going to take the formula that we found on the last slide and use that formula for carbon to find out how old some scientists believe a woolly mammoth remains would be. We're told here that the scientist estimates that only 3% as much carbon exists than when the animal was alive. So that's how much it's decayed. 3% is all that exists. So we're going to change this y into 0.03a. The reason we do that is because a is the initial amount, and the scientist estimates that it's 3% of the initial amount. So that's why it's 0.03a. And then we plug that in with the formula that we know, and we're going to solve again for the letter t to find out how many years old some scientists think the woolly mammoth remains are. So again, we have a's on both sides. We will divide both sides by a. So now to bring the t exponents down, we're going to take the log of both sides. I'm going to use the natural log because that's going to cancel off the e. So the natural log of 0.03 equals negative 0.00012t, and then we can divide by that small decimal number. Plug that into your calculator and you get an approximate time of 29,221 years. So that is how long ago, about 29,000 years, some scientists believe that woolly mammoths lived. Now that value could only be true if you make certain assumptions about carbon-14. Again, I just want to stress that I don't make those assumptions. I have a different worldview. So my value for this would be a little bit different. Either way, the calculations are correct for using exponential decay. Now just like there's a formula for exponential decay, there's also a formula for exponential growth. And that's when a quantity increases by a fixed percent each year or some other period of time. The values mean the same thing. The y is the amount of the growth, the t is the time, and it's in years unless otherwise stated. The a is the initial amount, where it starts, and the r is the percent of increase. This is also known as the rate of growth. So this is the formula and the values that we're going to use to find how things grow. Here's an example that talks about exponential growth when it deals with the population of a city. So we'll start with the formula, and we're going to plug in our values. Y is how much something has grown, and that's what we're looking for here. So we don't know what the y is, but we do know the initial amount of the population was 120,000. So that's going to be what we use for A. Our rate of growth is 1.5. Now that's a percent. As a decimal, we move the decimal 2 places to the left. So 0.015 is the number that we're going to use when we plug it in. And then the time we're talking about is from 1910 all the way to 2010. So the time is going to be 100 years. So we're going to use these values, plug them in, and solve for the y. Now there's really nothing magical about this formula. There's no logs that I have to take or anything. It's just a calculator problem. You do 1 plus 0.015, you take that to the 100th power, and you multiply it by 120,000. That's a calculator problem. Do that, and you're going to get 531,845.48. So that's an estimate of what the population would be at this growth rate after 100 years. Our last example is one in which we have a formula that's preferred by scientists for exponential growth. Again, y equals a times e to the kt. K is a constant. In this problem, we're told that in 2000, China's population was 1.26 billion and India's was 1.01 billion. They're both modeled by these two formulas. So we're actually given the formulas that model each one. The I of t is India over a certain amount of time, and the C of t is China over a certain amount of time. Now, we want to know when India's population will be greater. So we want to know when I of t, that function, is greater than C of t. And we want to know what time that will occur. So India's population is modeled here with this value, and we want to find out when that's greater than China's population, which is modeled with this value. And then along the way, we're going to solve for the t, and that should be able to tell us when it's going to happen. Now, to bring the t's down, we're going to take the log of both sides. I'm going to use the natural log, so the ln. Now, because of the product property of logarithms, when you're multiplying two logs, you can break that up and add the two logs separately. Now, the reason I do that is because I know that when I take the ln of e, since those are opposites of each other, those two things are going to cancel off. So now I have t variables that have been brought down from the exponent, and now I'm just going to solve this like normal. I'm going to subtract 0.009t from both sides. And then if I get the t's on the left, I'm then going to subtract the natural log of 1.01 from both sides, and wipe that off, and say that 0.006t is greater than the natural log of 1.26 minus the natural log of 1.01. And then finally, I'm going to divide both sides by 0.006, and that should isolate my t. So we end up with t is greater than all of that, which is a calculator problem. You're going to plug all that into a calculator, and you should get 36.86. So the question is, when will India's population be greater than China's population? And we would say in about 37 years. And since we started in 2000, it would be about 2037 is when that would take place.